So in the last video, we drew some patterns of electric field lines. We started with the electric monopole. So if we just had a single positive charge, we know the electric field lines point radially outward, indicating the direction of force on a test charge, which is by definition a positively charged object. So we said that electric field lines always originate on positive charges and terminate on negative charges. Somewhere else in space, there's a negative charge that this field line is going to terminate on, and likewise this field line, and so on. Another way of saying that the field lines originate on positive charges and terminate on negative charges, it would be equivalent to suggest that electric field lines point from regions of high something toward regions of low something. That something I'm thinking of is a term called electric potential. We'll learn a lot more about electric potential and how to calculate values of electric potential 2 chapters down the line in this course. But for now, it's a quantity we should become familiar with. Now notice I didn't say electric potential energy, I say electric potential. In the same way that electric field is related to electric force, because force is measured in newtons, and electric field is newtons per coulomb. In other words, electric field isn't force, it's force per unit charge. In the same way, electric potential is related to potential energy. Electric potential is potential energy per unit charge. It's measured in joules per coulomb. Okay. In any case, if it's true that electric field lines point from regions of high electric potential towards regions of low electric potential, then we can assume the electric potential at this point right here, P1, is higher than the electric potential here at point P2. However, we can draw in a point P3, and I want you to guess, how does the electric potential at point 1 and point 3 compare? Well, they're both the same distance away from the center of this charge. It turns out those 2 points are at the same electric potential. And the difference in electric potential between point 1 and point 2 is the same as the difference in electric potential between point 3 and point 2. Okay, so I can connect several points together and find a path along which the electric potential is constant. We call that a line of equipotential. And there's another line of equipotential here. Actually, I'm drawing them as lines, but in truth, these would be in 3 dimension, right? These would be like spherical shells. They'd be surfaces of equipotential, I guess, as opposed to lines of equipotential. And another line of equipotential here. You might be noticing something. The angle at which the electric field line intersects the line of equipotential is 90 degrees. That's true in all cases, and that'll be true not just for a monopole, but for any pattern of electric field lines compared to the associated lines of equipotential. Now, we said in the previous lesson that electric field lines can never cross or tangle or intersect, but the electric field lines definitely intersect the lines of equipotential. The idea of a line of equipotential is that you could take a charge Q and you could move it anywhere along this line of equipotential and no work would be done because there's no change in the energy per unit charge. But the amount of work it would take to move this charge Q let's say from point A to point B would be the same as the amount of work that it takes to move it from point D to point C. Even though it may be different paths, the change in the values of electric potential are the same from A to B as they are from C to D because they get you between the same 2 different lines of equipotential. Okay, so let's draw some pattern of lines of equipotential for some of the charge arrangements that we saw in the previous lesson. So let's go with the electric dipole. So we know the pattern of electric field lines. Looks something like this. What do the lines of equipotential look like? There's one line of equipotential that goes straight down and bisects this pattern. There's another line of equipotential, something like that. Notice wherever an electric field line intersects a line of equipotential, the angle is 90 degrees. There's another line of equipotential, looks something like this. Another one here, another one here, and so on. Okay. In a way, these are like the contour lines you see on a topographic map. If you've ever done any backcountry hiking or camping, not only do you need to know your north, south, east, and west, but you also need to know elevations. So you may have seen a topographic map that shows contour lines of elevation. Here we have contour lines of electric potential. The parallel plate capacitor. Field lines were uniform in the regions between the plates, and they start to curve near the edges because of the fringe effects. So the lines of equipotential would look something like this. Okay, so keep this in mind as you think about the direction of electric field lines. It's true that they originate on positive and terminate on negative, but that's interchangeable with this statement about electric potential.